Hello, audience at the Association for Behavior Analysis annual convention, virtually hosted at Washington, D.C. I'm sorry that I can't be with you live today due to time differences and some other commitments. But I'm going to summarize for you today in this invited address, which I'm very happy that the organizing committee chose me to do so. I'm going to describe my work into what's called SMART training, or strengthening mental abilities or relational training. And I'm going to do so under this very provocative title that refers to destabilizing stable traits, which is an obvious I can say this to this audience. Of course, behavior analysts often see the construct of traits as more of a barrier than as of an aid. I mean, it can be of use to think of intelligence as a trait in a very loose and temporary way, but of course it also inhibits research by encouraging psychologists to think of these traits as things that are unshiftable, and therefore to use intelligence testing as a way to identify children who cannot be helped as much as to identify children who can. And even when interventions are introduced with children who need help, to still see them as ultimately limited by their inherent intelligence. It's not an ethical approach in my view, and it's not a scientifically grounded approach in my view. So I'm using the term intelligence and IQ here very loosely as terms used by mainstream psychology, but which really here are just guides to orient us towards skill sets that we can enhance and make a really big difference on. So I'll start now by going through a little bit of RFT. If anyone's quite experienced with that, they may want to jump ahead a little bit, but I wanted to give some grounding to people who were new to the idea of using relational frame theory methods to enhance intellectual ability. But then what follows is a state of the evidence outline of everything published so far on SMART training and its effect on intellectual skills of various kinds and cognitive abilities and scholastic ability, scholastic aptitude, and also some in-press and under submission and in preparation work that's also happening in the field. I'm going to give you a very quick definition of intelligence. We can certainly define it how the mainstream do to begin with before we dismiss that. It's usually defined as the ability to learn, to understand, make judgments, or have opinions that are based on reason. Very poorly defined terms there, not technical for our purposes. It's defined as the ability or abilities to acquire and use knowledge for solving problems and adapting to the world. Okay, it's a bit intuitive. It's a set of skills that allow us to interact successfully with our environments. That might be a little bit more acceptable to the behavior analyst. Robert Sternberg says that viewed narrowly, there seem to be about as many definitions of intelligence as there are experts to define it. So it has been a very thankless task and one of the most controversial fields in psychology since its beginnings. So intelligence is assumed to be a stable trait. Certainly the fluency of the skill sets that are assessed by intelligence tests are relatively stable across the lifetime. There's a little bit of a smoke and mirrors involved in that. Of course, they are improving all the time, and that effect is known as the Flynn effect. But it's just that because it's your fluency rate at these various tasks is compared to that of your peers, and because most children advance at roughly the same rate, it looks like you're not relatively gaining any ground, and so your IQ, the quotient of the fluency of your various intellectual skills, appears to be constant. And of course, it's constantly moving, but not moving necessarily at a faster rate than anybody else's as you learn and improve fluency through schooling at a whole range of cognitive tasks: speaking, expansion of vocabulary, solving problems, and as we'll see, just generally speaking, deriving relations among stimuli, which seems to be at the core of almost all intellectual activities. So this is a circular argument, this idea that intelligence is a stable trait, because it's based largely on the stability of IQ scores that are observed using IQ tests that are not accepted as valid until the scores are stable. So in other words, when one is developing a new IQ test, one of the benchmarks for it being a usable test is that the scores are stable across time. And if you find that the scores are varying from test to retest, what you need to do is rejig your test, take items out, add items in, enlarge the size of the battery, or completely change all of the items so that the answers and the speed of answering on a particular subtest within the test doesn't change across time, or at least not at a faster rate than it does for one's peers. So IQ, though, is still a useful concept. It's a very crude index of general educational aptitude. Scores on IQ tests do correlate well with all sorts of governmental tests around the world, the SATs in the United States, the Leaving Certificate here in Ireland where I am, and so on. So it does give you you're taking a sample. You're sampling behavior of the type that you want to predict performance on. So it's somewhat of use. Of course, it gets dangerous when we assume that what we're sampling is G or some stable trait, because what it does is, of course, it changes the mindset of the psychologist, so that they end up using the test to decide which children cannot be helped, rather than deciding which children need to be helped and how. So we have this kind of contradiction going on in our educational system all over the Western world, where we use these assessments sometimes to identify kids with learning difficulties. We then may make interventions, but if you ask 99% of people who've administered those assessments, they will tell you they don't believe that they can raise the IQ of a child, and yet here they are doing all sorts of education interventions, presumably to mask that inherent lower IQ that the child has, which seems to me to be a very poorly scientifically informed way to approach this. So a functional approach to intelligence, this is, I suppose, a new way of talking about this kind of this third wave, as it used to be called, of behavior analysis, looking at it in terms of a more complex processes than perhaps were used in the Skinnerian approach to understand verbal behavior. Really, the term functional, it doesn't refer to functional analytic in the ABA sense. It simply just means what we've always been doing. It's that all our terms will be reducible to technical terms and to behavioral process, and we will avoid mid-level terms, and we'll aim for precision and control and influence over behavior. So just the summary term for that in my branch of psychology, which I used to consider to be relational frame theory, now I know it's known as other, is called the functional approach. And that in that functional, let's just say for now, the behavior analytic approach to intelligence, it of course won't merely describe measure and correlate intelligence indices with each other. It wants to understand the fundamental processes that underlie performance on those tests. Of course, mainstream psychology is interested mostly in these tests for purely how they predict other scores on other tests, how they predict performance in the applied domain in school, for example, and how they correlate with other measures. But we want to get underneath these tests and figure out what the processes are that lead to higher or lower scores on these types of tests. So, I have a problem here with my slides. Okay, here we go. So an obvious candidate fundamental process for this is derived relational responding. That's what I'm here to talk to you about today. Derived relational responding is the ability to derive relations between stimuli without direct training between the stimuli in accordance with a small family of what we call frames, such as equivalence. Stimulus equivalencing is relational framing. But organisms that are human for sure, and even non-human animals can respond to more than less relations, but as we'll see, not in an arbitrary way. So of course, a cockroach will pick a larger pile of food over a smaller pile of food, and that is a type of framing, but it's not arbitrary relational framing, which is the exciting bit, because this explains many complex human behaviors. And you have other frames such as opposition, for example. So yes, you can train your dog to go to the opposite side of a room, but that doesn't mean that they can respond to oppositeness in the abstract in other contexts. Derived relational responding may be so fundamental that it underlies or explains just about any form of complex behavior you want to pick, or at least largely explain most of the steps in the acquisition of those complex behaviors. So here's the well-worn description of equivalence, which at this point has become a cliche and a meme, and anything else you want to describe it as. We have here a dog in the top left, and the dog is named by a parent, and also the parent draws the child's attention to the printed symbol for the dog. So we might teach a child, for example, as was done by Murray Silman in his very first work, you point to a picture and ask the child to point to a word. So the child needs to point to the printed word DOG, and that's reinforcements delivered for that correct response. But then in another context, the printed word DOG is presented to the child, and they may be required to say the word. So the child will will utter the phrase, the sound dog, and reinforcement is delivered for that. And we can do this over and over again without ever actually reinforcing the utterance of the word dog in the presence of the picture of the dog. But what happens is that most children who are verbally able will fairly spontaneously produce these derived relations. This is the utterance of the word dog given the picture of a dog. They will often orient to or point to the picture of the dog when upon hearing the utterance of the sound, and all of the relations seem to be spontaneously reversible. So that is that when presented with the printed word of a dog, the child will point to a picture of a dog, even though that particular response was never reinforced. So with the classic Sidmanian description of stimulus equivalence, you train 2 relations among stimuli and you get 4 further relations back. In other words, a total set of 6 relations. So this was used quickly by relation frame theory to explain the generativity of language. That imagine how much a vocabulary could expand if it required so little training. Okay, multiple trials, but so few relations needed to be trained to get this whole gamut of other relations that become entailed by that training. Now, we're not going to get into the debate today about how this arises, but from the relation frame theory point of view, and there are other views, we think that this comes from multiple exemplar training. In other words, that the derivation is not itself really a novel behavior. The correct response needs to have been shown with other stimuli in similar contexts, probably across thousands of exemplars and maybe tens of thousands or even hundreds of thousands of trials. So I often joke that, I could talk about relation frame theory so much that I could write a book in it. And in fact, I have written a book on it. In fact, I've only edited these 2 books on relation frame theory for your, if you want to read about it in greater depth. But derived relational responding is established according to RFT through multiple exemplar training. It is a generalized operant that generalizes to stimuli that are not formally similar to the ones used during the multiple exemplar training, which is a concept that some people antithetical to RFT struggle with. We don't think it's in any way inconsistent with Skinner's view of the operant. An operant was never meant to involve merely the direct training of particular skills given particular discriminative stimuli that couldn't generalize. The generalization of an operant to different contexts is a part of the concept of the operant, and there was no requirement that the stimuli to which it generalized needed to be formally similar to the ones used during training. But here's an example of a task that will illustrate the distinction between arbitrary and non-arbitrary, or truly, fully, abstractly generalized derived relational responding. So we can teach an animal, any organism, any type of animal, human or otherwise, to select, let's say, the brighter of 2 bulbs. So we present a 5 amp and a 2 amp bulb to a child, and we say, point to the brighter one. If the child points to the 5 amp bulb, reinforcement is delivered. It's pretty easy. This is totally formal. There's no abstract relation responding required. We might do it again with 2 further exemplars, an 8 amp and a 4 amp bulb. The child points to the 8 amp bulb, reinforcement is delivered. That's correct. And so on. Now, to truly test the generalization of this operant skill, this relational skill, we can present a 9 amp and a 5 amp bulb. Now, if the relational responding is generalizing well, the child should pick the 9 amp bulb because it's brighter than the 5 amp bulb. But that is so even though the 5 amp bulb has been presented before and its choice was consequated with reinforcement. So in this particular case, the choice of the 9 amp bulb, if that is in fact what happens, shows that the operant of choose the brighter has generalized across exemplars to a novel set, even where it competes with direct a response that it has in the past been consequated by reinforcement. So here's another example. Which of these 2 coins is bigger? In Europe, just like in the United States, we have these contradictions in our coins. In our 5-cent coin in the euro system is actually larger than our 10-cent coin, despite the fact that it's worth less. So it makes for a good example. So a child can be asked which of these 2 coins is bigger. The answer is the 5-cent coin. That's very easy. It is formally bigger. That's not an arbitrary form of relational responding. The size between the coins is non-arbitrary. But if I switch the question to which of these 2 coins is more valuable, in the context of value, the arbitrary relation between the coins leads to a very different answer. The one that's more valuable is the one on the right, the 10-cent coin. And this is not so easy to teach a non-verbal organism. And I don't mean, maybe this is a good point to draw that that false distinction, of course, as the organism becomes verbal, what we mean is that they're able to do this, which means that this is what we mean by verbal. The ability to respond to these stimuli in terms of a derived arbitrary relation is what makes the response verbal. So, of course, the emergence of language and this ability are synonymous. One doesn't lead to the other. They are the same thing. So the 10-cent coin is greater than the 5-cent coin in one context. That's the context of value. But the 5-cent coin is greater than the 10-cent coin in a different context. That's the context of size. So now I'm introducing the concept of the contextual cue. It's a cue, some environmental cue that's present that selects out which features of the stimuli apply in this particular case that will guide responding. If the word that's present is size, if that's the contextual cue that's used, in the context of asking the question, point to the greater one, then I'll get one response. And if I change the context to value, I get a different response. So ipso facto, my contextual cue is functioning as such and controlling the derived relation responding. So multiple exemplar training occurs across caregivers, whether they realize it or not, across thousands of exemplars. In normal language, it's a naturalistic process. Parents that speak well and read and have large vocabularies will tend to spend more time verbally interacting with their children, and the child will acquire more extensive and more subtly contextually controlled verbal behaviors. So the word dog, for example, might be spoken. The parent may then point to the picture of a dog or require the child to do that. And in another context, to use the Irish language, they may use the word madra, which is the Irish for dog, and ask the child to again point to a picture of a dog or an actual dog. But the child will have difficulty in the early stages of deriving any relationship at all, any equivalence between the word dog and the word madra. But that's okay. The parent just tells them the answer. And they say, don't you realize we use both of these words to point to dogs, therefore they must mean the same thing as each other. And if it's a parent who themselves has been a history of reinforcement for multiple exemplar delivery, that is what we might call patience, then that's okay. And many, many more exemplars will be delivered across time. So we might do the same thing with a cow, for example. We have here a picture of a cow. The child in one context hears the word cow. The parent orients the child to the actual cow or picture of a cow. In another context, bow is spoken. The child is oriented towards the cow. The child will not show any derived equivalence. The parent will tell them that cow and bow must mean the same thing because they both refer to an actual cow, and on it goes. Other examples, pig, that goes with a picture of a pig. Muck, the Irish for pig, goes with the pig as well. The child has to be shown the derived equivalence, or in RFT as it's called combinatorial entailment, to refer to the same phenomenon, but with some bells and whistles that may become relevant in more complex analyses. We do the same thing with a horse. Horse and couple both refer to a real horse, therefore they mean the same thing as each other. And finally, one day, a child is presented with a picture of a hen. The parent refers to it as a hen. In another context, they refer to it as a kjark. And the child will derive combinatorially without assistance that the kjark and the hen must mean the same thing. But the important thing here is that the child has done nothing new. It's the teacher that has done something amazing. They have managed to create a generalized relational response across enough exemplars so that the child may have the experience of insight, but that insight, that deriving, has come directly from exemplars of the exact same kind with the exact same format, but with different objects, which is irrelevant. So the similar process could happen for teaching children what opposite means, what before it means, after means, hierarchy, and so on. So in a paper I think it came out in 2010, yes, with myself and Sarah Cassidy and Dennis O'Hora, we started to map out how an RFT account of intelligence might work. So we took some standard and common intelligence tests, both the widely used ones by educators, and then some nonverbal IQ tests like Ravens and various cognitive abilities tests. And we just started looking through the questions and asking, is it the case that most of these tasks on most of these tests seem to draw on a fairly small set of relational skills? And the answer was yes. It was quite surprising how easily it jumped off the page when you look at the items on almost any IQ test, how they involve some type of responding to one stimulus in some type of terms with another. And those terms were a very small set. So you're dealing with which of these stimuli is greater, lesser than, means the same as, means the opposite of, which month becomes before, which month comes after, and so on and so on. Or if X is a type of Y, what is a Z? And so there's a lot of this kind of hierarchical relational responding where you're responding to, a daisy is a type of flower, but a flower is not a type of daisy. And that kind of shows the non-bidirectionality of hierarchical relations and so on. And the IQ tests are replete with these types of tasks. So we figured, well, if you could hone the relational skills of a child across a whole range of relation frames, that is teaching them that if A is more than B and B is more than C, that C is less than A, not more than A, that many tasks on these tests might become easier. So we went about doing that, but in extremely rudimentary ways, I'll explain. So IQ tests we proposed in this paper in 2010 are largely tests for relational skills. So they test word equivalences, verbal batteries look at things like oppositeness, more than, less than. They look at metaphors, which are equivalences between equivalents. So a hand is to a glove as a foot is to a shoe, for example. Those are forms of more complex derived relational responding. And then in another study, now several years later, and we've had couple of these now, these correlational studies where we assess the fluency of this whole battery of relational skills, and then we run some IQ tests of different kinds in different studies and various cognitive tests that are often used, post-stroke victims, also to memory tests and so on. And we see if the scores on the relational skills test correlate with those. Now, that doesn't in any way prove causation, but it's just a starting point to confirm at least they seem to be tapping into the same type of skill set. And the answer is they do. In fact, just as an interesting take-home point, in the two studies that we published with Dylan Colbert as my PhD student in the last 4 years or so, we found that the relation abilities indices that we've developed, the main one is called the RAI, the Relation Abilities Index, which I'll come to. That's available online at our website, raiseyouriq.com, and we've published in several studies. That correlates with most IQ tests more than most IQ tests' own short form correlates with themselves. So in other words, we get a fairly reliable index of about 0.7, a 0.7 correlation between our relational skills tests and pretty much any IQ test you want to pick. But that's how much the WASI, for example, the brief WACE, correlates with the WACE, or Ravens correlates with the WASI, and so on. So these correlations are completely fitting. And of course, the cynic outside of our field will say, well, that's because, of course, smart people can do your derived relational responding tasks. But of course, we approach it a completely different way. We say, no, your IQ test depends upon these skills because we have the more fundamental process identified here. So here's an example with our Relation Abilities Index correlates 0.74 with full-scale IQ. It correlates about 0.78 with verbal, just in case you want to get a feel. That is the one that helps the correlation along quite a bit. Performance IQ doesn't correlate so well, but most forms of IQ, of subtests or subindices of IQ tests do correlate well with the Relation Abilities Index that we've developed. Working memory correlates to some extent, for example, as well. That's often used as an explanation for how some forms of what's called brain training or cognitive training may be enhancing IQ scores in some studies, although there's no definitive study yet aside from ours showing that that's even possible. But the explanation is that what you're really doing is just enhancing working memory, and you're helping someone perform better on the test, which is not quite full explanation, and it's also just doesn't seem to be the case. Yes, and here's the other study by Dylan Colbert et al., Malone, Barrett, and Roche, and this is a more recent paper in Perspectives on Behavioral Science that we expanded our relational skills battery and showed some interesting correlations between an expanded Relational Abilities Index test and several new tests that weren't looked at in the first study, and we get pretty much the same type of effects. We get full-scale IQ here is much lower in this particular study, and we learned a few things about types of relational skills that correlate better than others. It turns out that the ones that we guessed at the beginning of this program, that is same, opposite, more and less, are really important. And some of the more complicated, complex relational skills like hierarchy and metaphor were far less predictive of overall IQ than the core relational skills that you'd expect. And this is amongst young adults, not children. So our radical hypothesis is really not that radical at all. It's not even our hypothesis. It's naturally implied by a radical behavioral approach to behavior, supplemented by some relational frame theory contributions that got at some subtleties and forms of contextual control, which are very powerful, over derived relational responding that were added by RFT. And so this was just a natural suggestion that had to fall out of RFT, which is that deriving relations is a core process involved in many intellectual activities. And so increasing your proficiency at relational responding should lead to improvements in a range of cognitive skills. And those that constitute general intelligence should be no different. So I find it very interesting. It's worth just noting at this point briefly, in case you are discussing this with someone or you're pursuing this research yourself, it's amazing how receptive audiences are to the idea that behavior analysis has tools to improve reading. They'll go, yeah, I got it. I can see that. I can read the evidence for that. I can see how that would work. They're somewhat okay if you look at very specific things like syntax and grammar, attentional skills for sure, basic mathematical skills. They're okay with all of that. But as soon as you tell them that, when you put all that together, those things are what make up IQ. So we reckon we can increase intelligence as measured by IQ tests. They're taken aback and tell you that that's impossible, which is a very strange contradiction. It shows that disconnection between many psychologists' belief that everybody has competencies which probably can be enhanced. And yet at the same time, there being this limiting factor called G, which cannot be enhanced. And it really highlights the inconsistency in the reasoning of psychologists if they are not surprised that we can help with all of the components of intelligence tests, but are surprised if we can raise IQ. That just doesn't hang together. So in 2011, we published a study with Steve Hayes, myself, and my colleague Sarah Cassidy. That was from Sarah Cassidy's PhD. Sarah had come into me several years earlier and suggested, told me to put my money where my mouth was. You say in the RFT book, the purple book, that you should be able to increase intelligence by increasing the fluency of relational skills. Let's do it. And I was taken aback and said, yeah, that's only in theory, but to actually make that happen is going to be really, really difficult. I reckon that IQ tests in the full forms take a long time to do, and that leaves huge scope for test stability, because you have to shift the performance on all of the subtests and to a considerable degree to get an overall IQ gain. Messing around with the edges is not going to raise the IQ by any degree worth talking about. So I reckon we were up against some technical challenges to do with how well constructed the IQ tests were to guarantee that we got no changes. For example, the test-retest reliability of a test allows a taker to score a few extra points or lose a few extra points on one take compared to the other, and for that to be considered irrelevant. So that there's some elasticity allowed, of course, in the tests. Well, you're going to have to at least beat that. So even if you have a very real effect of 3 or 4 points for all of your participants, critics are going to say, but the test-retest allows for changes of 3 or 4 points from one take to another. It's not due to your intervention. And this is even when it's the case that all of your participant scores went up. Of course, what people forget is that in test-retest indices, the score also often goes down. In fact, it's almost half. So only slightly more than half of your participants will see a gain in IQ, and almost a half of your participants will see a drop in IQ from a test to a retest with no intervention. So we knew that getting gains for all participants of just a few points was not going to cut it. We were going to have to get very large gains, and that was very daunting. But that's exactly what we started to see with a very rudimentary intervention, which I'll quickly outline, participant after participant. So this is the form that it took. We present to a child these statements where A, B, and C are nonsense words. A is the same as B is opposite to C, is A the same as C. This is actually an experiment 2 that's the format we used in experiment 2 of Cassidy et al. 2011. The format in experiment 1, I don't have time to go into here. It was far more difficult for the child to learn because the words same and opposite were themselves abstract cues which we trained from scratch. But effectively, the task involved presenting what nonsense syllable A is the same as nonsense syllable B is opposite to a third nonsense syllable C, is A the same as C is the question, and if the child got it wrong, we simply told them the answer. A is opposite to B is opposite to C, is A opposite to C? The answer here is no. It's the same as C. If they got it wrong, doesn't matter. We told them the answer. And we just did that block after block after block until the child could pass 16 of these types of tasks in a row, 16 for same, 16 for opposite, 16 for more, and 16 for less, with no correction, and then get a new test with all new nonsense words and do it all over again with no feedback on any of the trials in a block of 16. If they got any wrong in the test, they went back to training again with feedback. So this is what a more than task would look like. A is more than B, C is less than B, is A more than C, with the nonsense words changing on every exemplar. If the child can't answer, that's okay. Just tell them the answer and keep going until they get 16 in a row correct, then go to a test with all new 16 new tasks of the same type, but not the same exact same format. So, for example, we can reverse some of those relations. We could ask, for example, A is less than B, C is more, less than B, and C is more than B, and then ask a question about any two of the relata, A and C, B and A, or B and C. So there's lots of ways you can mix this up. You do that within all of the parameters, select them randomly from within the parameters, and if the child gets 16 in a row correct, they get a test. If they fail the test, that is, get even one wrong, they're back to training. So it's really strict. In experiment 2, this is what the data looked like. We took some children, it was 8 children. We asked the school to give us children that had been given services and had not shown improvements. Basically give us the worst of your worst, the ones that you desperately need help with. The school suggested those children. We took their baseline IQs and we did the intervention over a period of months, a few times per week. And after a period of months, we took their IQs again. So 7 of the 8 had their IQs had risen by more than a standard deviation, which of course is way beyond what's considered achievable by most of the brain training literature. So we were pretty happy with that. While not peer reviewed, we did follow up those kids 4 years later, and those IQs basically maintained. And that's published in a book by Todd Kashdan on positive psychology. But as I say, not peer reviewed. So then we said, okay, this seems to be working. Let's do this properly. So we digitized the relational skill program. It had already been digitized, but it was just a clunky piece of software I had thrown together. But we put this online, so we created so that children could study at school, they could practice at home, and it was easier to control and collect data and so on. So we developed 55 relational training task types. That's 50 different levels of complexity of relational skills. Roughly half of them are for same and opposite, and roughly half of them are for more and less. So basically what we're doing is we're manipulating the parameters of the complexity of the tasks in tiny steps from stage 1 to stage 2 to stage 3 to stage 4. So stage 1, for example, might be A is the same as B, is A the same as B, in a really, really low level. Stage 2 might involve reversing, asking some questions about the reverse, the bidirectionality of that relationship. And then we would slowly build up. And it actually takes 5 stages to get to the first derived relation, where there are 3 stimuli involved. So blocks 1 to 29 are same opposite tasks. Blocks 30 to 55 are more than less than tasks. And subjects, like in Cassidy et al., they cycle between training and testing until they pass a block of 16 types of trials in a row with a new nonsense word on every single trial. So no participant ever sees the same nonsense word twice across any 2 tasks, across any of the relations, across any of their sessions ever. This is where quite complex coding comes in. So when the child logs out and logs back in, their nonsense word usage has been recorded, and it's not possible for them to ever see a nonsense word a second time, which means that every single exemplar is truly novel, and the software is randomly selecting amongst the various levels of complexity within each stage, which is already a very, very narrow level of complexity. So each task has unique nonsense words, and the child moves very slowly from each level of relational complexity to the next. So here's an example of what the child sees on screen in a sort of a gamified environment. Does is opposite to gel. Gel is opposite to left. Is does the same as gel. And that refers only to the first statement, as you'll notice. So that is basically asking them something that they've just, the reverse of something they've just been told in the first line. So is dull opposite to gel, or is dull the same as gel? The second statement is not even recruited in that task. But on another question at the same level, it might be. They might be asked about the relationship between does and left, for example. So there's a lot you can do with just 2 statements, and you can ask about the relations specified in the statements, or you can ask about other relations, like in this case, not specified in the statements. Here's a very complex task that comes very close to the end of the whole training. Left is less than sedge, gel is less than left, does is less than gel, is does more than left. That involves some derivation. And may I point out, it's only for this talk that you're seeing those nonsense words twice. A real child would never see these nonsense words twice. I just constructed this for the talk. So this 3-statement problem would always have unique nonsense words that the child had never seen. This is what it looked like, just to zoom back to show. So we've got a professor who's giving advice to usually a child. Adults can take this too, because it gets to such advanced levels. The more you train, the more fluent your relational skills become. So the child presses a yes or no button on every task. They have 30 seconds to respond. So we're trying to hone fluency, but keep it fairly liberal, because some of these tasks require almost the full 30 seconds. Only when the child has mastered all 55 stages can the clock be turned down, and then the child begins again and does a whole lot again, if the teacher or trainer has the patience, but with a lower time window. That timer there just shows the time clock counting down. This is from a different stage, stage 14. This is a 2-statement problem, 2 opposites statements, and the question is in terms of an opposite. In stage 18, there's 2 statements, but they're of different type. So there's an opposite and a same question, and in this case, the question does involve the first and third term, so there is some derivation involved. Stage 27, there are 3 statements, and they are, in this case, they're of a mixed type, and the question could be about either of those relations, a sameness question or an opposite question. So with that type of task, you have multiple questions that you can ask and multiple ways to present the task within parameters. The parameters are published, by the way, in a paper by myself and my colleagues, Dylan Colbert et al., 2016, in Learning and Individual Differences. So that is all public if anyone wants to take the protocol and copy it, and so on and so on. Here's stage 32. It's a 2-statement problem with more than tasks and a more than question. Stage 41, you can see the backgrounds are changing just to keep kids awake. 2 more than statements and a less than question, and so on and so on. Just it gets increasingly complex across the stages. Stage 53, really tough, because in this case there are 3 less than statements, but the question is about a more than, uses the contextual cue more than, which isn't actually present in the statements. So we conducted a study with that protocol online, and that was published in 2016. This is where we published the protocol for the whole thing, and we got some pretty exciting results, which I'm going to outline here. 15 children were used in experiment 1, which is rather small, but given the intensity of the training and the difficulty of managing it, it's, I hope, forgivable. They're administered the WISC UK pre and post. They have twice weekly training sessions. The teacher looks after that. We weren't involved in the actual training, and there was no control group because the class was actually that small in this very small rural school. The testers were not blind, so that's true. Here is what the results look like. Okay, so notwithstanding no control group, I'm speaking to behaviour analysts who understand variation in human behaviour, who work in educational contexts and do these types of assessments. These IQ scores, as I often describe it, because we've replicated this effect many times now, it's just about every child every time. Now that is really hard to say about any other type of intervention developed by psychologists to raise the intellectual ability of a child, even if it is temporary, which it's not, is to take every IQ and raise it by a considerable amount every time. So obviously that's statistically significant. There's a very large effect size. We're looking at effect sizes here of easily 15 points and more per child. So the child with the lowest IQ at outset was 84, theirs rose to 806. The child with the highest IQ was 119, and they rose to 140. Now, some research we've done in the meantime that's not published indicates to us that the gains do decrease with increasing IQ. Also, what happens, and this is not our own research, but it's out there, is that IQ also becomes more unstable from test to retest as the IQ goes up. So it's harder to extract effects with high IQ groups compared to control groups. But in this particular study, we still got very respectable IQ gains with the highest IQ individual. So in experiment 2, we took another group of children in a different school, in this case, a whole class of children, 30 children. They were aged 14 to 16. They were given the DATS, the differential abilities test, pre and post training. This was completely blind. They had twice weekly training sessions at school, but yet again, there was no control group. And the scores look a little bit like this, where the gaps are for kids who missed one of the assessments. So the pre-intervention bars are the dark ones, the post-intervention ones are the light ones, and the child's pre and post scores are side by side, obviously. So you can see mostly gains from pre to post, far noisier than for the IQ. This is something we see over and over again, by the way, for anyone interested in this research. The IQ tests are unbelievably stable. So when you get a gain, you see a nice clear gain, and you see it consistent across participants. When you get gains on aptitude tests that are using scholastic settings, you see huge variation in the gains. The data is very noisy, and you need larger gains to see statistically significant effects. No, I'm not impressed necessarily by statistically significant effects, but unfortunately some of our contemporaries are. And there's sometimes a game to be played with the statistics, which is a shame, because every kid every time is good enough for me. But unfortunately, it depends on whether t-test says yes or no. So relational frame theory, mathematical and logical skills, a multi-exemplar training intervention to enhance intellectual performance is a paper not published by me, which I'm delighted to say, but by Johan Theres and colleagues in Sweden. And they got quite modest gains using that exact same protocol in a study with children aged 10 to 11. 21 children were taken. They were randomly assigned to control and intervention groups. They were administered Raven, a non-verbal IQ test, pre and post, and a school developed maths test, which before they began, I knew they were not going to get improvements on because it's even more variable than a standardized aptitude test. So these are just school-based maths tests, but they got twice weekly training sessions. They gave them to the children. They were non-blind testers, pre and post, and they did have a control group, but it was passive. And participants were matched at baseline. So the effects were real, they were significant, but they weren't huge. You can see here on the progressive Ravens matrices, we have a very modest gain, but before you balk at how small it is, just a couple of points or more, this is the best that most brain training can hope for. So you take the dual NBAC test, which is just about the only other training system that has been shown to improve general IQ. It seems to do it by only targeting working memory. It seems to only show effects on tests like Ravens. With very large samples, they see gains of only about 2 points, and much of that is in controversy now because of several failures to replicate. So this showed that effect for the experimentals and not for the controls. It was not significant. They got no effects for the maths tests. So this exact protocol was also used by Jennifer Hayes and Ian Stewart, who's also here in Ireland, at the National University of Ireland, Galway. And Ian and his PhD student, Jennifer, took 10 to 11-year-old children, 28 of them, again assigned them to two groups. They were administered the WASI, the WIAT, and the WISC, WISC subtests for arithmetic, and some state aptitude tests for numeracy and literacy, pre and post training. They also trained their kids twice per week. There was blind test scoring, which is great, and there was an active control group. So we're getting better. And participants were matched for IQ across the two groups. So at this point, I'm just going through the data because the protocol is fixed. This is what the IQs looked like at baseline, 97 versus roughly 99. And afterwards, we see that fantastic divergence up to 107 for the experimental group and about 98 for the non-experimental group, the control group. Now, they received Scratch training, which is a coding tool developed at MIT for teaching children about coding, computer coding. It makes it fun, and it's widely discussed casually in the literature and openly by schools as if it were a fact that this is good for your logical reasoning and so on. And it turns out, at least in this study, it's not. And it was beaten hands down by an enhancement of relational skills method. So this is what the data looked at. I don't think we need to go into the details of this. Sorry. This is the table that Hayes and Stewart published. We can speed that up there for a second, showing the gains on individual components of the WASI, the WIAT, the WISC, and the Drumcondras at the bottom are the Irish state aptitude tests. So we see those for the experimental group, and we don't see equivalent gains for the control group. If anyone wants to rewind back or pause their video for that. These are the IQ tests, that I've already shown you. Getting a bit lost here in my slides. Not sure why this is happening. Okay, so another study done by myself and Micah Amand, who was doing his PhD at the time and did this study on the side, looking at the effect of smart training on children who are seriously socially disadvantaged in Bangladesh. The idea was these children have more than most children around the world need a leg up. They are getting some content, of course, at school and some basic skills, but they are often so far behind due to problems with poverty, missing huge amounts of school and massive social strife, that anything that would hone their learning skills, any basic intervention that would make their school more effective would be welcome. Knowing that they wouldn't finish the training, knowing that they would miss huge amounts of it, which is exactly what happened, we posed the question at the beginning so that we would look at obviously the effect of the training on pre and post nonverbal IQ scores with these children, but specifically look at the effect of the amount of training they received. And things worked out terribly for the children, but sadly it's exactly as we expected for the study, insofar as there was a small outbreak of civil strife during the study, and many children went missing. Some turned up many weeks later back at school, which often was the only place they got fed. And so we had huge variation in the amount of training, which we did want to look at the effect of. This is what the standard Ravens scores look like for the bottom quartile, next quartile, third and fourth quartile in terms of amount of stages passed in the training of the 55 stages. So baseline Ravens scores, that's standard Ravens progressive matrices, they did not predict score gain, which is interesting and exciting. Their age also didn't predict the gain, but the stages of training completed did predict the gain. And there was quite a high positive predictive value of 91. That's a large amount of variance caused by the training. So the training matters is the point. And this is on children aged 6 to 12. We did have to look at age as a variant, of course, in our regression analysis because the age of range was relatively wide. Okay, this next replication by McLaughlin et al. Is in press in the Journal of Behavioral Education. They used larger samples, which is great. We're moving in the right direction. 43 experimental and 27 matched controls. They were pupils aged 13 to 14 in a school that agreed to help with the study. And they do have an active control group. This time they used Scratch, just like the Hayes and Stewart study had done, versus smart training. And they matched those for hours, which is really important, as Hayes and Stewart had done. They measured nonverbal IQ using the K-bit, Kaufman's brief intelligence test, pre and post. And they measured processing speed, pre and post as well. So, jump to the results. Nonverbal IQ gains were modest. This is almost certainly because the amount of training undertaken was very, very low. The average amount of stages completed was only 16. That's not even a quarter of the training. It's a half of the first half. So it involves no more or less than training, only same and opposite, and at that barely half of the set, and less so for many of the participants. So you do see a nonverbal IQ gain of about 6 points, and you don't see the equivalent with the control group, who are a matched control, who are receiving an active intervention to help with their reasoning skills. But we don't see the gains in that case. Processing speed, you do see gains, but in both cases. So there's no significant gain there, a difference by group. And there was, however, a strong negative relationship between baseline nonverbal IQ and nonverbal IQ gain. And this is, this is where the research needs to go now. So I've presented several replications to you. Might have gotten a bit tedious there for a while. But what we really need to know now are the boundary conditions. And the next couple of studies I'm going to show you to finish up with are doing exactly that. So this study looks at whether nonverbal IQ can help explain some of the gains, and finds that it does. The lower the starting IQ, the larger the potential gains. Now that is in with a very narrow range because the gains were very small. So we would need that to be replicated with a good sample, but with amongst the range of participants who did actually finish the training, all 55 stages. Another study that's only in preparation is by Chuck Stryker, Colbert and Roche. That's in preparation. This is a study that was conducted in the United States, in the state of Pennsylvania. And what the first author intended to do as part of his PhD was to assess the effects of SMART on literacy and mathematics scores on a North American state aptitude assessment, which is where the research needs to go. We've done IQ now quite extensively and various forms of IQ and school aptitude, but what we need is to see if we can shift scores on tests that educators make decisions on that affect the future of an individual or access to resources. So Charles Stryker took 59 children, 15 to 17 years of age. They were split into two groups by the teachers, matched based on scores on the Pennsylvania Classroom Diagnostic Toolset, the CDT. There was a passive weight control group for those not assigned to the treatment group randomly. There was independent test administrators and training supervisors, which is all good. And 45 school days were needed from baseline to follow up. So that does not include weekends and break periods and so on. So it's about 10 weeks of training for each child. And actually, really nicely, every single child finished all of the training in this particular study, which is very important. So we won't create any myopic effects here if you don't give anyone a headache, but just at a glance, and you can pause the video afterwards to have a look. The treatment participants' scores for mathematics on the CDT can be seen on the top, and you can see that every kid, every time effect that I was talking about, with almost no exception, I think, for one. So you have the baseline scores are lower than the follow-up scores after the 10 weeks of training on a state test that is used to make decisions about the academic competence of children. And on the bottom graph, you can see the control participant scores, and you see that natural variance that you would expect to see from test to retest. You see lots of falls as well as small gains and overall smaller changes. As for the reading scores on the CDT, the top group again is the treatment group. The black bars are the baseline bars, and you can see there's a bit more variance here, but generally speaking, almost entirely gains for participants. And the opposite for the control group, the passive control group, where you do see some gains, but you also see some falls, and the change is overall smaller. So the maths score growth, these are standardized state level maths test scores that are used in that state and similar tests in other American states to decide on the need for services for a child. You can see the maths growth score is very low for the control group, but for the experimental group down here, you can see the gain is considerable and is approaching a standard deviation on that test. So these are potentially life-changing score changes for these children. So the maths score changes by group can be seen here. The dotted line is the treatment group, the solid line is the control group. There's quite a lot of variation in scores as measured by standard error, but we still have a significant gain, by the way, on an analysis of variance. There is an effect over time for the treatment group, and there is the slight change over time. It does vary by group. So an ANCOVA, I should say, used the baseline scores as a covariate to extract that effect. And these are the reading scores to change by group. Not quite matched as well, but very well matched at baseline, not different at baseline. Controlling for baseline differences if they exist using an ANCOVA, the effect is also there for the reading scores across time. That is, it rises dependent on the group in which the participant participated. And finally, another study that's just being written up at the moment by Ian Gray and my former student, Dylan Colbert, who's the second last author, and myself, Bryan Roche at the end, and two colleagues of Ian Gray's in Abu Dhabi. They used the exact same typical Cassidy et al. Online smart training protocol as all the other studies did. And what they aimed to look at was another boundary effect, the effect of baseline attentional skills on the SMART effect. Again, sort of just preempting the types of questions that critics are going to ask us if we as behavior analysts say we have a functional analysis of intelligence in terms of the fluency of derived relational responding skills across a small set of particular patterns of those skills, which we call relational frames. And we think that enhancing the fluency of these will push the intellectual skill set such that that's reflected in IQ scores, and they're going to say, what the? And they're going to ask us for evidence that it's not all sorts of spurious things like test-retest effects and students buying into the program and placebo effects and all of that. And one of those things they often mention is baseline attentional ability. They're really all you're looking at here is that kids that have higher attention skills, they benefit more from these types of interventions regardless of what they are. So this is just the beginning of that inquiry. We took 32 kids aged 10 to 11 in English-speaking schools in Abu Dhabi. It was easier to assign one school who volunteered one classroom full of kids, a very small class, to be in the study, and to assign one of those to the experimental group and take the other school, picked randomly, and assign them as the control group, rather than having every second kid within the classroom. Now, with hindsight, that's what we should have done. The schools were terribly matched. We didn't suspect that at the beginning. They were, for all intents and purposes, the same kind of socioeconomic level. Nothing pointed to the fact that the IQs at baseline of one group should be different to the other, but they were drastically so, which was disastrous. So we did randomly assign the schools to conditions, but they weren't matched. We measured attention of all of the children on the 3 indices of the TEACH, that is a test of everyday attention, and the WASI was used to measure IQ pre and post training. The groups were terribly badly matched, with the IQs being so different at baseline that it was basically impossible to close that gap at follow-up with the intervention. But nevertheless, this study proceeded. And here's what you have on this graph is the full-scale IQ of the experimental participants. And you can see that effect again, every kid, every time, at the very least, bar the first one, whose IQ remains stable. In fact, what actually happened was that particular participant is that they never turned up for the follow-up assessment, so we inserted a equal IQ to baseline to assume no change. And the control participants, you also see some change in full-scale IQ, but you also see lots and lots of drops. So it's far from every kid every time. In fact, I think we might have more drops than gains there. So we used an analysis of covariance to look at this effect, whereby the IQ of the control group dropped. That's a weight group, not active. It dropped across the training period, which is about 10 weeks, 2 sessions per week, about 45 minutes each. And we see the gain in IQ by the experimental group, but even after intervention, the gain in IQ of the experimental group doesn't bring them up to the baseline even of the control group, which is terrible. So we ran an ANCOVA, analysis of covariance, to control for baseline IQ. There was a significant difference between the pre and post IQ scores for the experimental group, while controlling for all 3 baseline attention index scores simultaneously. The adjusted R-squared is 0.38. So that gives us a good idea of how important attentional scores is to the effect of the training, which all children finish, by the way, as well, which is very important. There was a weak relationship between selective attention and IQ, which is one of the 3 indices if you want to break it down, and strong relationships between sustained attention and everyday attention and the IQ gain. So there was no such effects for the control group. So look, to wrap up, this is what the normal distribution of IQ scores looks like. Of course, the test is constructed so that the average is 100 for ease, but there's nothing stopping us in behavior analysis, certainly not with what I've been doing with the SMART intervention of the past decade or so, to suggest that we can't completely destroy that curve and shift all children upwards, and even adults, towards a mean IQ of what is currently about 120. And then if we want to rescale the scores and just call that 100, that is absolutely fine. But there's nothing stopping us, it looks like, enhancing children's relational skills so that they perform better on just about any test you want to imagine that is used in educational or psychological assessment contexts. I know it's still early days. We don't have the big RCT. I'm not sure any big RCT will ever be good enough based on my experience, but that is coming. There are plans in the pipeline for larger studies, and there are studies under review at the moment from other labs that are larger samples than what I've reported here. So we need replication, we need larger samples, we need to study boundary effects. But while I'm not going to preempt the reliability of this data at this point, based on whether some higher ranking journal I've been publishing and accepts the data or not. It may be that this was a series of coincidences. We do need to confront that possibility. But using scientific and laboratory experience, looking at the different types of measures we've used, thinking in terms of a reticulated model of science, everything is triangulating in on the fact that something's going on with the SMART training. It's shifting repertoires considerably, and I think it's one of the best investments we can make is to push this type of inquiry using this method or others. There are other systems like the PEAK system and other just simple ABA, straight up ABA programs that can enhance the fluency of a whole range of these skills. If we can push the IQ button for mainstream psychology, they are really going to listen. And we do have the tools now, and I hope you agree that we're onto something really special with this relational frame theory approach to enhancing intellectual skills, or if you want to index it with a test that may be more or less useful, IQ, if you like, or intelligence. Thanks for your time. I hope you get something out of this, and please don't be afraid to contact me at the email address that I'll put up now. And of course, thanks to my colleagues, especially Dylan Colbert and Sarah Cassidy over the years, and many other colleagues who know who they are, who've participated in all sorts of ways over the years with this research to make it as exciting as it is. Enjoy the rest of the conference, and I hope to meet you all someday in person at ABAI.